Welcome to our journey into the fascinating world of plate tectonics. Have you ever wondered why earthquakes happen or how mountains are formed? The answer lies beneath our feet in the shifting plates that make up the Earth's outer shell. Today we'll explore how these massive slabs of rock move, interact, and shape the surface of our planet. By understanding plate tectonics, we unlock the secrets of volcanoes, ocean trenches, and even the drifting of continents. Let's dive in and discover how this theory revolutionized our view of Earth's dynamic nature. Plate tectonics is the scientific theory that explains how the Earth's outer shell, called the lithosphere, is divided into several large and small plates. These plates float on the semi-fluid layer beneath, known as the asthenosphere. The movement and interaction of these plates are responsible for many geological events and features, such as earthquakes, volcanoes, and mountain ranges. This theory has become the foundation for modern geology, helping scientists understand the ever-changing nature of our planet. To understand plate tectonics, we first need to look at the structure of the Earth. The planet is made up of several layers: the crust, the mantle, the outer core, and the inner core. The crust and the uppermost part of the mantle form the lithosphere, which is broken into tectonic plates. Beneath the lithosphere lies the asthenosphere, a softer, more fluid layer that allows the plates to move. This layered structure is crucial for the movement and interaction of tectonic plates. Lithosphere is the rigid outermost shell of the Earth, while the asthenosphere lies just beneath it. The lithosphere is broken into tectonic plates which move over the softer, more ductile asthenosphere. This movement is driven by heat from the Earth's interior, causing convection currents in the mantle. These currents push and pull the plates, leading to the dynamic processes we observe on the surface. Tectonic plates are massive slabs of solid rock, both continental and oceanic, that fit together like a jigsaw puzzle to cover the Earth's surface. There are 7 major plates and many smaller ones. These plates are constantly moving, though usually at rates of just a few centimeters per year. Their boundaries are sites of intense geological activity, including earthquakes, volcanic eruptions, and mountain building. 7 major tectonic plates include the Pacific Plate, North American Plate, Eurasian Plate, African Plate, South American Plate, Antarctic Plate, and Indo-Australian Plate. Each of these plates covers vast areas of the Earth's surface and interacts with neighboring plates in unique ways. The movement and collision of these plates shape continents, create ocean basins, and drive the formation of mountains and volcanoes. The edges where tectonic plates meet are called plate boundaries. These boundaries are classified into 3 main types: divergent, convergent, and transform. Each type of boundary is associated with specific geological processes and landforms. Understanding these boundaries helps explain why certain regions are prone to earthquakes, volcanoes, or mountain building. Divergent boundaries occur where 2 tectonic plates move away from each other. This movement creates new crust as magma rises from the mantle and solidifies at the surface. The most famous example is the Mid-Atlantic Ridge, where the Eurasian and North American plates are moving apart, forming new ocean floor. Divergent boundaries are often marked by rift valleys and volcanic activity. Convergent boundaries are found where 2 plates move toward each other. This can result in one plate being forced beneath the other in a process called subduction, or the plates may collide and crumple to form mountain ranges. The Himalayas, for example, were formed by the collision of the Indian and Eurasian plates. Subduction zones are also sites of intense volcanic and earthquake activity. Transform boundaries occur where 2 plates slide past each other horizontally. The movement is not smooth, and stress builds up until it is released as an earthquake. The San Andreas Fault in California is a well-known example of a transform boundary. These boundaries are characterized by frequent earthquakes but typically lack significant volcanic activity. What causes tectonic plates to move? The answer lies in the heat from the Earth's interior. Convection currents in the mantle, created by the transfer of heat, push and pull the plates in different directions. Other forces such as slab pull and ridge push also contribute to the movement. These processes work together to keep the plates in constant motion, shaping the surface of our planet. Convection currents are the primary force driving plate movement. As heat rises from the Earth's core, it causes the mantle to flow in slow, circular patterns. Hot material rises, cools as it nears the surface, and then sinks again. This continuous cycle acts like a conveyor belt, moving the tectonic plates above. Without these currents, the plates would remain stationary and Earth's surface would look very different. In addition to convection currents, 2 other forces help move tectonic plates: slab pull and ridge push. Slab pull occurs when a dense sinking plate pulls the rest of the plate along as it subducts into the mantle. Ridge push happens at mid-ocean ridges where new crust forms and pushes plates apart. Together, these forces drive the complex motion of Earth's plates. The theory of plate tectonics is supported by a wealth of evidence. Fossil records show similar species on continents now separated by oceans. The shapes of continents fit together like puzzle pieces, especially Africa and South America. Geological features such as mountain ranges and ocean ridges also align across continents. Modern technology like GPS allows scientists to measure the movement of plates in real time. For plate tectonics, the idea of continental drift was proposed by Alfred Wegener in the early 20th century. He suggested that continents were once joined together in a supercontinent called Pangaea and have since drifted apart. While Wegener's theory lacked a mechanism, it laid the groundwork for the development of plate tectonics, which provided the missing explanation for how continents move. Seafloor spreading is a key piece of evidence for plate tectonics. At mid-ocean ridges, new oceanic crust is formed as magma rises and solidifies. This process pushes older crust away from the ridge, causing the seafloor to spread. Magnetic patterns in the rocks on either side of the ridge provide a record of this process, confirming that the ocean floor is constantly renewing itself. Most earthquakes occur along plate boundaries, where the movement of plates causes stress to build up and eventually be released. The type and intensity of earthquakes depend on the nature of the boundary. For example, transform boundaries like the San Andreas Fault are notorious for frequent, shallow earthquakes, while subduction zones can produce powerful, deep earthquakes. Volcanoes are closely linked to plate tectonics. Most volcanoes form along convergent and divergent boundaries where magma can reach the surface. Subduction zones in particular are known for explosive volcanic eruptions, as water and other materials are dragged into the mantle and melt, creating magma. The famous Ring of Fire around the Pacific Ocean is a prime example of volcanic activity at plate boundaries. Mountains are often formed at convergent plate boundaries where two plates collide and the crust is pushed upward. The Himalayas, Andes, and Alps are all examples of mountain ranges created by the collision of tectonic plates. This process, called orogeny, can take millions of years and results in some of the most dramatic landscapes on Earth. Ocean trenches are deep, narrow depressions in the ocean floor, formed at subduction zones where one plate is forced beneath another. The Mariana Trench is the deepest part of the world's oceans and a classic example of this process. Subduction not only creates trenches but also leads to volcanic arcs and intense seismic activity. Not all volcanic activity is linked to plate boundaries. Hotspots are areas where plumes of hot mantle material rise to the surface, creating volcanoes in the middle of plates. The Hawaiian Islands are a famous example, formed as the Pacific Plate moved over a stationary hotspot. Hotspots provide further evidence of plate movement and the dynamic nature of Earth's interior. Plate tectonics has played a crucial role in shaping Earth's history. The movement of plates has caused continents to drift, oceans to open and close, and mountains to rise and erode. These processes have influenced climate, sea levels, and even the evolution of life. By studying plate tectonics, scientists can reconstruct past environments and better understand the forces that have shaped our planet. Throughout Earth's history, continents have come together to form supercontinents only to break apart again. Pangaea was the most recent supercontinent, existing about 300 million years ago. Before Pangaea, there were others like Rodinia and Gondwana. The cycle of supercontinent formation and breakup is driven by plate tectonics and has had a profound impact on global climate and biodiversity. Wilson cycle describes the repeated opening and closing of ocean basins caused by plate tectonics. This cycle involves the formation of new oceanic crust at divergent boundaries, the movement of plates, and the eventual destruction of crust at convergent boundaries. The Wilson cycle helps explain the long-term evolution of Earth's surface and the distribution of continents and oceans. Movement of tectonic plates has a significant impact on Earth's climate. The position of continents affects ocean currents and wind patterns, which in turn influence global temperatures. Mountain building can also affect climate by changing atmospheric circulation and increasing weathering, which removes carbon dioxide from the atmosphere. Over millions of years, plate tectonics has helped drive major climate changes. Shifting of continents and the formation of new landforms have influenced the evolution and distribution of life on Earth. Changes in climate, sea level, and habitat availability, all driven by plate tectonics, have led to mass extinctions and bursts of new life. The isolation of continents has allowed unique species to evolve, contributing to the planet's incredible biodiversity. Today, scientists use GPS and other technologies to measure the movement of tectonic plates with incredible precision. These measurements show that plates are still moving, reshaping the Earth's surface. For example, the Atlantic Ocean is widening as the American and Eurasian plates move apart, while the Pacific plate is slowly shrinking. Understanding these movements helps us predict future geological events. Earthquakes are one of the most dramatic consequences of plate tectonics. When plates grind against each other or collide, stress builds up until it is suddenly released as seismic energy. This energy travels through the Earth as waves, shaking the ground and sometimes causing significant damage. Understanding plate boundaries helps us identify regions at risk and develop strategies to reduce earthquake hazards. Volcanoes form when magma from the mantle reaches the surface, often at plate boundaries. Eruptions can be explosive or gentle depending on the type of magma and the tectonic setting. Volcanic eruptions can have far-reaching effects, from creating new land to altering global climate. Studying volcanoes helps us understand the power and unpredictability of plate tectonics. Tsunamis are giant sea waves often triggered by underwater earthquakes at plate boundaries. When a large section of the seafloor suddenly moves, it displaces water and sends waves racing across the ocean. These waves can travel thousands of kilometers and cause devastation when they reach land. Understanding plate tectonics helps us predict and prepare for these powerful natural disasters. Movement of tectonic plates has concentrated valuable resources such as minerals, oil, and gas in certain regions. Mountain building, volcanic activity, and the formation of sedimentary basins all play a role in creating these deposits. Understanding plate tectonics is essential for locating and managing Earth's natural resources. While plate tectonics creates beautiful landscapes and valuable resources, it also poses hazards. Earthquakes, volcanic eruptions, and tsunamis can cause loss of life and property. By studying plate tectonics, scientists can identify high-risk areas and develop strategies to reduce the impact of these natural disasters. Modern technology allows scientists to monitor plate movements in real time. GPS, seismic networks, and satellite imagery provide detailed data on how plates are shifting. This information is vital for earthquake prediction, volcanic monitoring, and understanding the ongoing changes to Earth's surface. Plate tectonics affects human society in many ways. From the location of cities and resources to the risks of natural disasters, understanding plate movement is crucial for planning and safety. Engineers and architects use this knowledge to design buildings that can withstand earthquakes, while governments develop policies to protect communities. While predicting the exact time and place of earthquakes or eruptions remains challenging, advances in plate tectonics have improved our ability to forecast where these events are likely to occur. By studying plate boundaries and monitoring seismic activity, scientists can provide early warnings and help communities prepare. In regions prone to earthquakes and other tectonic hazards, engineering plays a vital role in reducing risk. Buildings, bridges, and infrastructure are designed to withstand shaking and ground movement. Advances in materials and construction techniques have made it possible to save lives and minimize damage during natural disasters. Educating people about plate tectonics and the risks associated with it is essential for building resilient communities. Schools, governments, and organizations work together to raise awareness, teach safety measures, and prepare for emergencies. Knowledge is one of the most powerful tools in reducing the impact of tectonic hazards. Some plate boundaries are especially well known due to their geological activity. The San Andreas Fault in California, the Mid-Atlantic Ridge, and the Himalayas are just a few examples. These regions are studied extensively to better understand the processes at work and to improve hazard preparedness. While Earth is the only planet known to have active plate tectonics, scientists are searching for evidence on other planets and moons. Mars, Venus, and some moons of Jupiter and Saturn show signs of past or limited tectonic activity. Studying these worlds helps us understand the uniqueness of Earth and the possibilities for tectonics elsewhere in the solar system. Plate tectonics will continue to shape Earth's surface for millions of years to come. Continents will drift, oceans will open and close, and new mountains will rise. By studying these processes, scientists can make predictions about the future of our planet and the challenges and opportunities it may bring. The presence of plate tectonics is one of the features that makes Earth unique in the solar system. It plays a vital role in recycling materials, regulating climate, and supporting life. Understanding this process not only deepens our appreciation for our planet, but also guides the search for life elsewhere in the universe. Scientists continue to study plate tectonics to answer unresolved questions. How did plate tectonics begin? What controls the speed and direction of plate movement? Ongoing research uses advanced technology, computer models, and field studies to uncover new insights and refine our understanding of this fundamental Earth process. Plate tectonics is a core topic in Earth science education. Teachers use models, experiments, and interactive tools to help students visualize plate movement and understand its effects. Learning about plate tectonics inspires curiosity and encourages the next generation of scientists to explore the dynamic nature of our planet. In summary, plate tectonics is the unifying theory that explains the movement of Earth's plates and the geological activity we observe. From earthquakes and volcanoes to the formation of continents and oceans, this process shapes our world in countless ways. By studying plate tectonics, we gain a deeper understanding of Earth's past, present, and future. Plate tectonics is more than just a scientific theory, it's a key to understanding our planet. It explains natural disasters, resource distribution, and the evolution of landscapes and life. As we continue to study and learn, plate tectonics will remain central to our quest to understand Earth and protect its inhabitants.